1, 2, 3. All right, into Merman's chapter 1, which is entitled The Principle of Relativity. Clearly, this must be an important principle that we're going to discuss because we're going to be talking about Einstein's special theory of relativity for most of the course. So let's get into this and think about what the word relativity means. It means at the same time something that's kind of familiar and also a little bit unfamiliar, so it will take some practice in thinking about. So let's start out by just imagining that we're on a long train trip and we've gone to sleep in our sleeper car and woken up in the middle of the night, and we look out the window, and by the dim moonlight we can see that there's a parallel track next to ours, and all we can observe is that the train on the parallel track is moving to the left from our point of view at a certain speed. And the question I want to ask is, which direction is your train moving from which you're observing this? And I'm often going to ask these kinds of questions where there are multiple answers that you might choose. And what I want you to do is make a definite choice about which one you believe in at this point. It doesn't matter whether you're correct or incorrect. But if you need more time in thinking about it than I'm giving you in this video, you can always pause the video before continuing on. So make a choice now. And in this case, the correct answer is, from the information that's given, it's really impossible to tell which direction your train is moving. It could be moving to the right, could be moving to the left relative to the ground. It could be at rest relative to the ground from all the information that's given there. And this relates to the principle of relativity in that, it's sort of hard to tell fundamentally when one is moving. So I'm going to give a bunch of statements, different kinds of wordings of the principle of relativity. One of them could be stated this way: one cannot tell by any experiment or mental introspection whether one is at rest or moving uniformly. And here uniformly means moving at a constant speed in a constant direction, so along a straight line path with a constant speed. So in the train example, this means you can't tell if you're moving or uniformly or at rest. Now, in this case, of course, on a real train, you can tell if you're at rest or moving, because when you're at rest, there's not as much vibration, or maybe there's no vibration, whereas when you're moving, there's a certain clickety-clack from the tracks. But here we're imagining maybe an idealized magnetic levitation train that doesn't have any vibration, or even more idealistically, if we're out in deep space and we're in some sort of spaceship that's moving along, just coasting through space, and we do an experiment, we won't be able to tell from the outcome of the experiment whether our ship is fundamentally at rest or fundamentally moving in a certain direction. So what we can observe when we look out the window of our spaceship, of course, is our motion relative to other objects, or their motion relative to us. In relativity, we don't really distinguish between those. They're two different descriptions of the same thing. But what's important is there's no fundamental sense to the assertion that I am the one doing the moving and the other thing that I'm observing is at rest, or the other thing is the thing that's moving and I am the one who's at rest, or perhaps that both of us are moving relative to each other but neither of us is at rest. The assertion of the principle of relativity is that none of these is fundamentally true. Each one could be true from a certain person's point of view, but none of them is absolutely true. Let me just put down a couple other slight variations on the description of the principle of relativity. If you perform two identical experiments under identical conditions, except that one is done in a laboratory, for example, with no windows in it, so you can't see the outside world, that's at rest, and the other one's done in a uniformly moving laboratory, the two experiments will have the same outcome. Another way of saying this a slightly different way is that if you consider the laws of physics as summarizing all identical experiments that could be performed in two different laboratories, the laws of nature would be found to be the same in a laboratory that's at rest and one that's in a laboratory that's uniformly moving. Another way of thinking of this is that there's no fundamental difference between being at rest and moving uniformly. So when I say I'm at rest, it's just something that's sort of a biased point of view from one observer, but it's not something that's absolutely true. Another way of even sharpening up this a little bit more is that, physicists, when they consider a laboratory at rest or a vehicle or an object at rest, we would consider that to be a special case of an object that's moving uniformly. In other words, if you're moving at a constant speed in a constant direction, you're moving uniformly, and when you're sitting at rest, that constant speed is 0 meters per second or 0 miles an hour. So the laws of nature are the same in any uniformly moving laboratory, and that includes ones that are at rest. So that's what the principle of relativity says. It says that there's no way to perform an experiment that tells fundamentally whether you're moving or not. Let's go back to the train example and try to tease out a few different ways that we could observe a train moving to the left as we look out the window. In this case, I want to imagine I look out the window. The train adjacent to me is moving to the left at 16 meters per second. And let's see how we could be moving in lots of different ways and observe this. For example, is it possible that my train that I'm observing from is at rest, and I look out the window and I see the train moving to the left at 16 meters per second? In other words, how would this freight train that I'm seeing be moving relative to the ground if mine were at rest? And the answer, of course, is that it's moving at 16 meters per second relative to the ground, right? I'm just sitting there and I see it moving by. That's easy. Is in the same situation, so it's still moving at 16 meters per second relative to the ground, is it possible that my train could be moving to the right at 16 meters per second, and I look out the window and see a freight train moving to the left at 16 meters per second? If it's possible, how would that freight train have to be moving relative to the ground? And this case is not too hard to imagine either. If I'm moving to the right relative to the ground at 16 meters per second, if I look out my window and look at something at rest, it's going to seem to be moving at 16 meters per second to the left. So in this case, the answer is it's at rest with respect to the ground. Those are easier cases. Let's try a few more challenging ones. Suppose I know somehow, maybe I'm looking at a speedometer on the train, I know that my train is moving to the left at 16 meters per second relative to the ground. Is it possible that I look out the window and see the adjacent train moving to my left at 16 meters per second? And the answer again is yes. What would that train have to be, how fast would it have to be moving with respect to the ground? Well, if I'm moving in 1 second relative to where I was at the ground, in 1 second I move 16 meters to the left, but the train that I see out the window moves 16 meters even more ahead of me. It would have moved 32 meters away from the point that I started at. So I can conclude it's moving at 32 meters per second relative to the ground. Let's try a couple more, just because this kind of moving back and forth between different points of view can be kind of confusing. Suppose I look out the look out the window, I see that the adjacent train moving left at 16 meters per second, and somehow I know that my train is moving left at 10. Is that possible? Well, yes. In 1 second, I move 10 meters to the left. The train I'm seeing moves an additional 16 meters to the left, so that means it would be moving 26 meters in every second. Okay? A couple more. Suppose I know my train is moving right relative to the ground at 4 meters per second. I look out the window and I see that 16 meters per second to the left. If I were looking at something that weren't moving, I would see it moving at 4 meters per second. So in 1 second, it would progress by 4 meters to my left. This one's progressing 16 meters to my left, so it must be moving an additional 12 meters beyond where something at rest would have moved in 1 second. So that means it must be moving at 12 meters per second relative to the ground. I think there's one more. No? I guess that's it. We're not used to thinking back and forth between different points of view, but fundamentally, the principle of relativity asserts that all of those are correct descriptions. There's no one true description of the state of motion of objects. For example, here's just a different way of viewing the same thing. Suppose one person observes balls A and B here. Ball A, from the point of view of one observer, is moving to the right at 6 meters per second, and ball B is at rest. Maybe this is the point of view from someone riding along on ball B, right? They just say, I feel like I'm completely at rest, and I see someone moving to the right at 6 meters per second. A second equally valid description of this state of affairs or state of motion of the objects would be that, and you can think of this as the point of view of from someone riding along with A. If someone's riding along in A, they think, I feel totally at rest. I'm just sitting here. When I look out my window, I see B moving to the left at 6 meters per second. So these are two different but completely equivalent descriptions. There's no fundamental truth to saying B is at rest or A is at rest. A third person might observe this from the point of view of moving to the right in the first picture at 3 meters per second. If they're moving to the right at 3 meters per second, they'd see B moving to the left at 3 meters per second, and A still gaining 3 meters to the right every second. So they would see both of the balls moving. And similarly to someone moving left at 3 meters per second in this first situation, they would see B moving to the right at 3 meters per second and A moving to the right at 9 meters per second. So the important thing about this is that each of these descriptions is equally valid. None of them is more true than the other one. Each of them has just as much claim on truth as the others, and so therefore we'll say none of them is true. They're just different relative descriptions of the state of motion of these objects. The principle of relativity is saying that there is no way to experimentally determine which of these is true. And so therefore, in a sense, there is no sense of being absolutely at rest or moving. There's only relative motion of objects. And finally, maybe a more pointed way of saying it is that objects can move relative to each other. In all four of these cases, these objects are moving relative to each other, but there's no sense in which objects are moving relative to space itself. If there were a sense, then we'd be able to say, well, one of the objects might not be moving relative to space at all, and it's fundamentally at rest. Principle of relativity says there's no such thing. There's no way to experimentally observe it or determine it, and therefore it does not exist. They're all completely equivalent, but different ways of observing the same thing. We're somewhat familiar with this sense of feeling at rest even when you're moving uniformly. Just when we think about astronomical observations of our local section of the universe, we know our Earth is spinning once around its axis every 24 hours. Maybe if you're on the equator, you would go exactly one Earth circumference in every 24 hours. If you calculate what distance you move there from the radius of the Earth, you find out you're moving about 900 kilometers per hour. We're moving incredibly fast with respect to the center of the Earth, 900 kilometers per hour, and yet to us it feels like we're at rest right now. Similarly, the Earth is moving relative to the Sun at 100,000 kilometers per hour, and the solar system, in other words, the Sun itself and all the planets with it, is moving at 800 kilometers per hour relative to the center of the Milky Way, and yet we notice none of this motion. We feel like right now that we're fundamentally at rest. So the principle of relativity says we can observe our motion relative to the other objects, but we don't have any sense or any experiment that we can perform that tells us whether we're fundamentally at rest or moving uniformly. We're going to get a lot of mileage out of that principle, believe it or not, in this course. Now I know that idea of moving back and forth from different points of view and trying to imagine how you would observe the speeds of different objects from different points of view is a little bit unfamiliar. So the worksheet, which should be on the website in PDF form, is going to help us practice with that in a simple kind of context. The idea with the first worksheet problem, which we'll do together just to get the basic idea, is that we've got two equal mass balls. One of them we'll color black and the other one white. And the idea is they're really bouncy balls, like those rubber balls that when you bounce them on the floor, they almost come up to exactly the same height. When I was a kid, they called those super balls, but whatever they are, they have the following property. If they come at each other with equal and opposite speeds, like is shown in the before picture right here, and they collide with each other, they're going to move away from each other with equal and opposite speeds after they've collided and not lose any speed from going to the initial to the final state. So if they're moving at 2 meters per second relative to the center before, they'll be moving away from each other, each going at 2 meters per second in the after state there and there. Now, here's a question. Suppose I know I've got some perfectly elastic balls of equal mass, and instead of observing them coming towards each other with equal and opposite speeds, instead I see one at rest and the other one coming in at a speed of 10 meters per second toward the right. And the question is, can I conclude anything about what the final state has to look like, given that I know that they're perfectly elastic, and that means in this symmetric case that they sort of bounce away from each other with the same velocities they came, or same speeds they came in with, but opposite directions. Here's how we're going to think about it. We're going to imagine this is the case, that this is what someone is observing from a certain point of view, and we're going to imagine this is the point of view of what you see happening in a train station. And we're also going to imagine what someone on a train that's moving by this at a certain speed in a certain direction would see. And we're going to try to make them see this initial state here. And if they see this initial state, we know they're going to see this final state, and then we'll try to transform back and see what our final state should be. So, for example, let's imagine a train going by the station. So in the station, this is what we see in the initial state. We imagine a train going by in the station to the right at 5 meters per second. If they're looking at a ball that's stationary in the station, they're going to see it moving to the left at 5 meters per second, right? And if a train moving to the right at 5 meters per second observes one moving to the right at 10 meters per second, they're going to see that ball gain 5 meters on it going to the right every second. So they'll see the white ball going to the right at 5 meters per second. So in the station point of view, this is the one we want to figure out. We have this mysterious initial state and we want to find out the unknown final state. But from the train's point of view, we have exactly the situation that we assumed we knew, because we know these are perfectly elastic balls. So the train is going to observe one going to the right at 5 meters per second, the other one going to the left, and of course we know because they're perfectly elastic, they're going to leave with those same speeds. They don't lose any energy in the collision. Now the question is, if we know the train is observing this, what will someone in the station see? Well, if the train looks out and sees the train is moving to the right in the station, if they look out and see something moving to the left at 5 meters per second, that's the same as saying that that object would be at rest in the station. So the white ball should be at rest from the point of view of the station. Whereas if the train looks out, it's moving at 5 meters per second relative to the station, and it still sees something moving ahead of it at 5 meters per second. That object, the black ball, would be moving at 10 meters per second relative to the station. So, as unfamiliar as this might be to most of us, if perfectly elastic balls, one's coming in and the other one's at rest, in the final state they actually exchange their velocities. In other words, the one that was moving ends up at rest and the one that was at rest ends up moving. That's only in the case where they have equal masses, so they're kind of identical elastic balls. So that's one example of how you can use the principle of relativity and say, well, let me reason about it from another point of view. And oftentimes adopting that other point of view is a little bit unfamiliar to us, but we're going to get some practice with it now in the other two problems that are on this worksheet. So what I want you to do is stop the video, or the video's ending right here. Stop it, work out on the other two problems on the worksheet, and when we come back together, we'll discuss the solution to them.